So let us talk about graphs. So we have already seen trees. Graph is also a non-linear data structure like trees. In fact, graph is also a tree. So since you already have dealt with tree, you have already dealt with graphs. So graph is also a tree. So what is a graph? Form of data structure that connects various nodes in a different form. Though in the tree we had a fixed structure that there should be a parent, then there should be a child, and the flow is always from top to bottom. Graph is a data structure that is completely free, that has no structure. Any element could be anywhere, any number of nodes can be connected. There could be one path, there could be two paths, there could be multiple connection. In fact, it has no rules, no parent child relationship. It could be cyclic, or it is kind of a free data structure that is actually used in various kinds of problem. In fact, graph we are actually using in a daily life. We are using graph almost every second. So graph has lots of use cases. In fact, if you talk about web is also connected, is a connected graph. Say one page is page 1, HTML page 1 is connected to page 2. Similarly, it could be connected to page 3. Page 1 could directly be pointing to page 3. There could be another page 3 would be pointed from 4. So this could be a flow, this could be a linking of various pages. So World Wide Web is also a graph. Another good example is a Facebook. So let us say this is you, this is your friend 1, let us say Amit, you are connected to each other. Another friend is let us say Sunil. Another could be ABC, it could be DEF. DEF and Amit could be connected to each other, and let us say there a new person comes and you want to get connected. So there you send a friend request, and there's a link between them and you, and is already connected to ABC, and Sunil is also connected to ABC. So there could be various kind of relations. So this is a graph. Facebook is a graph, Twitter is a graph. You follow someone, he follows you back, and various kind of relationship is there. In almost all social media is actually a graph where you are connected to each other via various kind of links. So let us talk about what is actually a graph. So graph, it is actually a collection of nodes arranged in some order, so without any rules. So let us say Amit is a node, and the connection link, we call it, this could be a link, this could be a edge. So we'll also go through what is a graph theory, and graph theory calls it edge. So you can call it link, you can call it edge, you can call this thing a node, or if you go to graph theory, it call it vertex. Yes, so I think you got the idea what a graph is. Graph is also a tree. It's a non-linear data structure. It's a non-linear data structure. Regarding linear, we all know that linear data structures are linked list, array, queue, stack are all linear data structure. We are talking about non-linear, and we got this idea about this graph. Computer science has borrowed lot of information from discrete mathematics. Here too we'll be seeing the graph theory in both maths and in the computer science. The definition for both of them is same. So we can represent a graph something like this. So graph is actually a collection of vertices and edges. So the V for vertices and G, yes, so node we call it vertex. So node can be also called as vertex, and link can be also called as edge, or or link. So graph is collection of vertex and nodes. So there could be multiple edges, there could be multiple vertex getting connected through multiple edges. Now to present this in, let us say this case, v1, I am having v1 over here, v2, then v3, v1 v3 are connected, v4 is there, v5 is there, and let us say v3 and v4 are connected. So this would be presented in something like this: v1, v2, v3, v4, v5. Yes, so that is a collection of vertices, and to represent E we'll be having something like this. So v1 and v2, to present edge we would be using the connection actually. So here v1 v2 is a edge, v2 v3 is a edge, v1 v3 is a edge, because so v3 v4 v4 v5, and that's it, I think. Yeah, so this is how we present vertices and edges. So this is what graph theory is. Now let us see what is a directed and undirected graph, or you should call it edges. So first of all, understand what is a directed edge. A to B. So we have a direction over here. This is A, this is B. So this is a directed edge. Okay, now let us talk about undirected edge. So if you see over here in this directed edge, you are given the direction where traversal can be, source and destination can be set. So if you see, there is only one movement possible, A to B. In this use case, source to destination is given over here, source to destination. Now if you see in the case of undirected edge, you are not given a direction. You can either travel from A to B, it could be A to B, or B to A, both could be possible, but in this case you can only travel in one direction, that is A to B. So this is what a directed edge and directed edges is, and a graph where all the edges are directed. Let us say this use case C, D, E. Okay, now if you see, I have given direction to all the edges. So this is a directed graph because all the edges are directed. You can call it digraph or a directed graph. And consider this use case, let us say F, G, H, and let us say we have I. So in this case you can see that there is no direction, so you can either travel from here to here, or you can move from F to I or I to F. There is no source destination, either could be source or destination. Okay, so this is what about digraph or undirected graph. Now this was his undirected graph. Okay, weighted graph and unweighted graphs. So what a weighted graph is actually an example of a Google map. Let us say we have city A, there is a city B, there is a city C, and D. So you want to reach city there and you have direction with it. This is a graph. Or let us also include E. There is a path from E to C to E to. Yeah. So this is my graph. Now to go from A to D, you need a path from A to D. This is a simple use case of Google Maps. So if you want to go from A to D, you will be going, you need a path from A, B, C, D. This is a path that you will be requiring. But now Google Maps also provide you the distance. Now to provide you distance, you must be knowing that when to move from city A to B, you would be requiring to travel 100 kilometers. From B to C, you would be required to travel 200 kilometers, and from C to D, you will again be required, let us say, 120 kilometers. So the weight of A to B is 100, B to C is 200, or C to D is 120. So whenever you see a use case in a Google map, you would be you try to relate it with a weighted graph where you are giving weight of each link or weight of each edge connecting two nodes. There could be multiple use cases too. There could be okay, we'll dive into those use cases. later on regarding Google Maps, but this is what a weighted graph is. Weighted graph or unweighted graph is a graph that doesn't have the weight. Let us see how we can represent graph. There are two ways to present the graph. One is adjacency list. Yeah, adjacency list. Another is adjacency matrix. So we'll see when to use which use case, which of this graph presentation. So if we talk about adjacency list, let us take this example. I have this graph 1 2 3 4 5 let us connect this to this, and this to this is also possible. Now to present this data in adjacency list, what I'll take is there are 5 nodes, right? So first of all, create 5 element array. I took an array of 5 elements. This first position presents the first node 1. So this is my node 1. Now in adjacency list we used a linked list to know the relationship between its neighbors. So now we have this 1. Now to let us know that what are its neighbor, I'll be creating a linked list out of it. So linked list would be something like this. 1 is connected to 2, and also connected to 1 is also connected to 5, so it would be somewhere over here. That's it. Similarly, 2 is connected to 1, 5 and 3. We'll draw over here 1, 5 and 3. Similarly, 3 is connected to 2, 5 and 4. So I'll take 2, 5, 4. That's it. Now talk about 4. 4 is connected to 3 and 5. 3 and 5. 5 is connected to 1, 2 and 4. 1, 2, 3 and 4. 5 is connected to 1, 2, 3, 4. So this is one way of presenting the neighbors of a node. So this presentation is called adjacency list. Now let's also see what is adjacency matrix, and we'll identify when to use which presentation. Okay, so this is what adjacency matrix is. So adjacency matrix is a matrix. So matrix, we all know, is something like this. I need 5 nodes, 3, 4, 5. Similarly, 5 nodes over here, 3, 4, 5. Now since there is no node from 1 to 1, there could also be a use case when a node could be pointing to self, that is a self loop. But right now in my case I do not have such connection, so I'll set 1 to 1 is 0. So node 1 has no connection with itself, node 2 has no connection with node 2 itself, node 3 has no connection with node 3 itself, putting it 0. Node 4 has no connection with itself, so 4 to 4 is 0. 5 to 5 is again 0. There is no connection. Now let us see again. So from node 1 to node 2, is there any connection? Node 1 to node 2 has a connection, so we put it 1 over here. Node 1 to node 3, does this have no? There is no connection, it is 0. Node 1 to node 4, there is no connection, let us mark it 0. Node 1 to 5, there is a connection, it should be 1. Similarly, node 2 to 1, there is a connection. So you always remember this is an undirected graph. If there had been only this 1 to 2, there has been a direction 1 to 2, then this would be 2. There is no path from 2 to 1, so this would be 0. But currently there is nothing such marked, there is undirectional, so we will consider that 2 to 1 there is a path, 2 to 0, 2 to 2 there is no path, 2 to 3 there is a path, so let us mark it 1. 2 to 4 there is no path, so let us mark it 0. 2 to 5 there is a path 1. Now let us to count from 3. So 3 to 2, 3 to 5, 3 to 4. 3 to 1 there is no path, 0. 3 to 2 there is a path. 3 to 3 there is no path. 3 to 4 there is one path, and 3 to 5 there is one path. Similarly we do for 4. 4 is connected to just 3 and 5, so rest all 0. 5 is connected to 1, 2, 3, 4 connected to all 1, 2, 3, 4. So if you notice this, this is a dense graph actually, because there are lots of connection between the nodes. And if you are able to understand these things, there are lots of ones over there. The data is too much connected, the nodes are too much connected to each other. So this is what a dense graph is. So in such use cases you will be using adjacency matrix, and this would be a sparse matrix. Adjacency list can also be called as can be used as sparse, because there would be very less connections to each other. So in the cases when their nodes have less connections, it is a sparse graph, then there you would be using adjacency list, or if it is a dense graph you would be using the adjacency matrix. Now let us talk about the space complexity. Can anyone please let me know what is the space complexity of adjacency list, and similarly space complexity for this use case, this adjacency matrix? Five nodes, so space that I took over here is 5 into 5, that is 25. So it would be n cross n. Space is n squares, and same is the time complexity required for it. Now I am leaving this for as an assignment. What is the space complexity if you have a sparse graph or using adjacency list?